Jim Malis again. Let's talk. Let's talk about some of the content that we're doing. We finished the last time the old practice exam number 1. Now let's look at old practice exam number 2. And like I said, guys, just labeled wherever you are, the mathematics is the mathematics. The mathematics is the mathematics. The algebra is the algebra. No matter where you're taking this class and what language you're learning it, it is what it is in that regard. So we're doing old practice exam number 2. Let's see what we can do here, guys. They talk about substitution and elimination method. Not really difficult stuff. There's a number of ways to do these. You can use matrices and determinants to solve systems of linear equations of any size. If you have n equations and n unknowns, some of the algebra we're talking about right now is pertaining to that, I guess you could say. If you are solving n equations, if you're solving for n equations in n unknowns, that is doable. You have to have at least as many equations as you have unknowns, and the equations have to be linearly independent. You can't have equations that are identical to one another. Even if they don't look like they're identical to one another, they may be identical to one another. If that's the case, they're not linearly independent. You need to have equations that are all linearly independent of one another, and if there's n equations and n unknowns, then you can solve for all n of those unknowns that are present. We're typically going to be solving for 2 equations and 2 unknowns and 3 equations and 3 unknowns. So let's kind of go there and proceed. They got this thing called the substitution method, that they got this thing called the elimination method. We're not going to get into matrices and determinants, but there is some really beautiful mathematics pertaining to matrices and determinants. Perhaps at another time, in another context, we could look at something like that, okay? For us right now, it's not going to be something that's absolutely imperative for us. All right, with that having been said, we have, there's a problem here, let's say problem number 1 from the practice exam number 2, and it's saying this. All right, they're saying this guy right here. How do you do this? How would you do something like this using the substitution method? And you can also do it using the elimination method as well. So substitution method is you solve for one of the variables, and then you plug one of those variables into the equation. Let me show you. Maybe I'll do a little bit extra on this thing to kind of see where we're going to go with this. Tell you what I'm going to do. Let me solve for x and then plug in that solution right here. So with this right here, why don't you subtract 6y on each side, and you end up getting, add a negative 6y on each side, and you end up getting negative 6y plus negative 31 is equal to x. Then you plug that x right into here, into this x right here, and then you end up just solving. It's going to be in terms of y, and then when it's in terms of y, you guys, it's going to be something very doable. This stuff is easier done than said, so let's just do it. Go right here. 3x is negative 6y plus negative 31 plus 5y. We got this right here. 3 times negative 6y is negative 18y. 3 times negative 31 is negative 93. All right, I mean, the rest should be pretty basic stuff, guys, that we're making moves on. Let's see what we can say here. negative 18y and positive 5y is negative 13y plus negative 93 equals negative 41. Okay, let's see where this is going to go. Add a positive 93 on each side. Add a positive 93 on each side, and you are getting an answer on the order of 52. Divide by negative 13 on each side. Y equals negative 4. Come back here. Put y equals negative 4 right here. Put y equals negative 4 right here, and it's going to spit out what x is equal to. So what you got is x is negative 6y plus negative 31. They have told us y is negative 4. What's negative 6 times negative 4? Got that. Add them up. Got negative 7. What just happened here? Well, we just solved this is what happened. X equals negative 7. Y equals negative 4. So, like I said, guys, I'm going to try to pick and choose how I go through some of this stuff. Our time constraints and circumstances aren't the best. You guys already know that. You've been there yourself. Got a lot to do as well. But let's try to know as much as we can about this stuff, make sense out of it. This is the answer, guys, via the substitution method. X equals negative 7, y equals 4. What does that mean? X comma y is negative 7 comma negative 4. Remember we were talking about linear equations earlier. That's the answer, that's the answer. It means the same thing. What does that mean? Well, here's kind of the interesting thing about this, if this makes any sense at all, guys. This right here, for that one right there, that system of 2 equations and 2 unknowns, if you were to graph each of these linear equations, if you were to graph this linear equation, write it in the form of y equals mx plus b, take this guy, write it in the form of y equals mx plus b, graph the two. When you graph them in two-dimensional space, you will find that they will intersect. You know where they're going to intersect in two-dimensional space? They're going to intersect right here. Nobody's asking you that right now, but I figure I might as well do this. We can get a lot of this stuff out of the way and be done with this, I guess, sooner rather than later. I mean, it gives you a little less to worry about. All these problems that are in there, you can do all of them via the means that I'm showing you. If you can do one of these problems correctly, either by the graphing method or the substitution method or the linear elimination method or the elimination method, graphing, substitution, or elimination, those 3 methods, if you can do it, you're fine. Well, I'm going to show you all 3 methods right here. We just did the substitution method to get right here. And there's what we got for an answer. I'm going to ask you something. Here's the question. Take this guy right here. Take the guy right there. Solve for y and write it in terms of y equals mx plus b. Take this one guy right here, equation number 1, let's call him. Let's call this guy equation number 2. Take equation number 1 and solve for y. What do you say you subtract x on each side? Subtract x on each side, that's negative x or negative 1x, plus a negative 31. Divide by 6 on each side, that's going to distribute, ladies and gentlemen. Well, here is, this guy right here is mathematically identical to this guy right there. They are mathematically identical. This is written in a more or less standard form or general form. I think there's a terminology for it. It's kind of escaping me right now. That's not really relevant. This is very much a general format of how to write a linear equation. And this is the slope-intercept form for writing a linear equation when you're talking about two-dimensional space, when you're talking about two equations and two unknowns. Now come over here to this guy. Do the same thing with this guy. Take this guy and add a negative 3x on each side and then divide by 5. So let's add a negative 6x on each side. Right, yeah, that should be right. Add a negative, let me see, I think I did something here I should not have done. Add a negative 3x, rather, I'm sorry. Add a negative 3x on each side, okay? Add a negative 3x on each side, you got to here, divide by 5 on each side. All right, well, they're not exactly the easiest linear equations to look at, but here you go. I got two linear equations that I'm going to graph, and I'm going to see where they're going to intersect. Again, I cannot emphasize this enough, you guys. This right here pertains to this guy. And this guy right here pertains to that guy over there. Period. Know that. All right, that's great. Now what do you want to do? Well, my goal is to see this again. I did this, and I did it with the substitution method, and I got this solution. Now what? Well, let's see. All right, what do we got here? We got y equals all right, guys, let me do something here. Let's build a t-chart. This obviously, I mean, there's some, 2 points determine a line. I'm not going to say cheat, but let me kind of make it a little bit easier. You see the fractions we're dealing with; they're a little bit out of control here. Let's see something here. Let's see something. X, Y. Let's see what we got. Let's put a 0 in there. I guess it's a pretty easy one to look at. 0 is a nice number to put in there, I guess, right? Let me see what I can do here. Put a couple here. Okay, 0 here, you got negative 31 over 6. Put a 0 here, that's 0, that's negative 31 over 6. That's negative 5 and 1/6. All right, not the greatest in the world here, but try to think of something good here. Let me put a, try to think of something here. It's gonna make it, let me put a negative, I'm gonna have to, there's not room on the t-chart, guys. Let's put something else here. I'll put a -1 right here. -1 times negative 1/6 is 1/6. 1/6 and negative 31 over 6 is 30 over 6. That's 5. Let me keep going here. Let me kind of keep the t-chart going. It's the same t-chart. I just ran out of room. Again, that was an easy number. Those are relatively easy numbers to look at. Relatively easy numbers. I think I might have done it wrong though. Let me. That's -5. I'm sorry. look what happened. You put a negative 1 right here. Negative 1 times negative 1/6 is positive 1/6. Positive 1/6 and negative 31/6 is negative 30 over 6. Negative 30 over 6 is negative 5. Okay, that's better. Let me kind of cheat. Not really cheat, but let's say, hey man, I guessed negative 7. I wonder if it's going to spit out negative 4. Here's a big one. Here's negative 7. Put a negative 7 right there. Negative 7 over 1 times negative 1 over 6 is negative times negative is positive. That's 7 over 6. Negative 7 right here. Negative 7 times negative 1 over 6 is positive 7 over 6. Positive 7 over 6 plus negative 21 over 6 is negative 24 over 6. Negative 24 over 6 is negative 4. That's interesting. All right, remember that. I got 3 points here, guys. 3 points, but this guy, for some reason, is of interest to me because it looks like that. Let's do it again. Put a 0 right here. 0 here. This divided by this is negative 8 and 1/5. Let me see if I can. Some are easier than others to look at here. Any 2 points would give me the equation of a line. I tell you what, let me quote unquote cheat a little bit here. Let me put a negative 7 in here and see what happens. You know what I think is going to happen. I think you know what's going to happen. We're going to get this. Let's see what we got. Put a negative 7 right here. Negative 7. Negative 7 times negative 3 over 5. Negative 7 over 1 times negative 3 over 5. Let's see what happens. Negative 7 over 1 times negative 3 over 5. Negative 7 times negative 3. Negative 7 times negative 3 is positive 21. 1 times 5 is 5. So negative 7 times negative 3 is 21. 1 times 5 is 5. It's positive 21 over 5. Positive 21 over 5 and negative 41 over 5 is negative 20 over 5. Negative 20 divided by 5 is negative 4. Okay, that's very much of significance. They're occurring in both tables. The negative 7 comma negative 4 occurs in both places. If you were to graph this guy, this has got a negative slope. It slopes upward to the left. This has got a negative slope. It slopes upward to the left. Let's see what happens here. Let's see what happens here. You're looking at it from scratch and see what we can do. I mean, you got 0 comma negative 5 for this. We'll do this guy first. This guy first. This guy pertains to number 1. This guy pertains to number 2 as far as the numbers of the equations here. We got that. 0 comma negative 5 comma 1/6. So 1, 2, 3, 4, 5. Here's 6. You go a little bit more. So 0 is right there. Negative 1 comma negative 5 is right here. And negative 7 comma negative 4, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, comma negative 4, 1, 2, 3, 4, 1, 2, 3, 4, so negative, right, something like that. Any 2 points determine a line, you guys. This is by far not a good drawing, but it's roughly indicative of a line. It's doing a little bit of curve I don't want it to be doing, but there you go. The other one is this guy. It's negative 8 comma, so 1, 2, 3, 4, 5, 6, 7, 8. Got this. And the other guy, and that's negative 7 comma negative 4. There you go, ladies and gentlemen. Where does it intersect? It intersects at negative 7 comma negative 4. Negative 7 comma negative 4. That's the solution here. If you drew these 2 lines using any points that are on each line. Get the points, pick randomly any points that are on line number 1. Graph those points, draw a line through it, you got a straight line. Graph all the points that are on line 2. Graph those points, draw a line through it, those points are on line 2. Where those two lines intersect is -7. Where those two lines intersect is -7, comma -4. So it's this guy right here. Where they intersect is -7, comma -4. It doesn't, I mean, I happen to purposely choose -7, which spit out -4 right here for equation 1. I chose -7 right here, and it also spit out -4 for equation 2. So they had something in common. Even if I didn't put -7, comma -4 on there, theoretically, if you could draw the perfect graph, if you could draw the perfect graph, bam, the intersection would be right there, -7, comma -4. So this is the graphing method. It gave you the same solution that the substitution method gave you. Period. It's as simple as that. It's as simple as that. You kill a lot of birds with one stone when you know how to do that stuff, you guys. All right, sounds good to me. Let's stay with these guys. Let's stay with these guys and start erasing some of the stuff that's on here. But I'm going to stay with these guys. I'm not going to go substitution method now. Now I'm going to do the elimination method. Now I'm going to do the elimination method. Well, let's leave that up there. You're going to get the same answer. You know you're going to. I mean, look, the purpose of mathematics is solving problems. There's no point to employing certain mathematics if the mathematics is not going to be consistent every time you're doing the mathematics correctly. The mathematics works because you're doing it consistently. Okay, let's see what's going on here. All right, let's start. Let's start it again, guys. We've got the situation of equation 1, equation 2, and I'm not going to do anything much. I'm doing a thing called the elimination method. Here is an instance where you eliminate one of the letters, solve for the remaining letter, and then plug it back into one of the two equations, or one of however many equations there are. Doesn't matter into what equation you plug it back into. As long as the equations were initially related in the whole process, you can plug in to those and get the answer. That won't be an issue. Because both equations satisfy the answer. If it is presumed that there's an intersection taking place, and you plug in variable or variables that solve things initially, you can plug it into any one of the three because they all have a common solution. So if they have the one or two or however many variables in common, if they have all those variables in common, they're going to have that quote-unquote last variable in common, no matter which one you choose. They're all going to have that commonality, so it doesn't matter which one you plug into because they're all going to the same place. Let's make a long story short here for you guys. A number of ways you can look at it. You kind of use your your good judgment when you're doing this stuff. But typically what I do in the setup of these things, if there's an x, I call it 1x. If there's a negative x, I call it negative 1x. Here you go. You've got the two equations. I've separated them for a reason. You'll see what I'm about to do. Tell you what I'm going to do. I'm going to take the top equation and multiply by -3 on both sides of the equation. And I end up getting this. So I multiply by -3 on both sides of the equation. Then I'm going to take this guy and leave him alone. You kind of pick and choose where you want to go. Sometimes you got to multiply both equations to be able to knock somebody out. If there would have been, let's say, if this would have been like a 2x and this would have been a 3x, I'd have to go 2 times 3 is 6. I'd have to shoot to get a 6. So I'd have to multiply by 3 on each side. Here I'd have to multiply by 2 on each side and then look to get something to happen. Okay? So we got it to here. We got this right here. You got it to here after you do the mumbo jumbo that you're doing. Add the two equations. You're purposely eliminating one of the variables. What is negative 3x and positive 3x? It's 0. What is negative 18y and positive 5y? It's negative 13y. What is 93 and positive 93 and negative 41? That's 52. All right. Divide by negative 13 on each side. Y equals negative 4. Well, I guess I was kind of waiting for that to happen. I want to get the same answer. There's no point in doing mathematics if you're not getting the right answer every time. I don't care what mathematics you do. I don't care how you do it. Make sure your mathematics is consistent and that you work hard and that you pay attention to detail and you're accurate. And the mathematics is accurate, consistent, valid. Doesn't matter what methodology you're using. You're going to get the right answer. I don't advise using the graphing method to get an exact solution. If you could perfectly graph something, you would perfectly get the right answer. You can see I can't perfectly graph stuff, so you're probably better off just going substitution or elimination method. Theoretically, the graphing method, in strictly speaking, is going to give you the right answer if you could graph perfectly. Y is negative 4. If y is negative 4, you can go back in to one of the original equations. If y, there is a y equals negative 4, what x is associated with that, either one of the equations will get you there because they do intersect. If you're looking at it graphically, they do intersect at a particular x and y value. So for this y value, there's a unique x that works. You could use either one of these guys to get you there. Let's use this one. It's purposely a little more difficult. Let's use 3x plus 5y equals negative 41. Okay, sounds good to me. Let me put, I don't know what 3x is. So let's kind of, we can play this a whole bunch of ways, I guess you could say. We don't know what 3x is because we don't know what x is. We do know what y is. It's negative 4. Five times negative 4. 5 times negative 4 is negative 20. Add positive 20 on each side. Divide by 3 on each side. Wow, this is all looking pretty familiar, isn't it? X equals negative 7. Y equals negative 4. It's as simple as that. Well, it's the same. It better be the same answer. The math is the math. Remember what we said, guys. Answers don't change. Answers don't change if you do different mathematics. If there is a mathematical problem that has a unique solution, that's it. It's got a unique solution, and you're going to solve it. You're going to get it right. And any way you do it consistently will get you there. Simple as that. So that's 3 ways for you. There was the graphing method, substitution, and going to work. They're all going to work. Let's go. I mean, they got some great problems here. I mean, and we're going to figure it out how to go here. They've got. Let's go to problem number 8, and they talk about some things. For number 8, it's 3 equations and 3 unknowns. Well, believe it or not, those are also linear equations, but they're linear equations in 3-dimensional space. And their linearity is not really discussed or not really expressed by lines the way we're used to seeing lines, the way we saw them up here. They're expressed by planes, like a plane figure, like this desktop is a plane figure. So the board, the blackboard, the whiteboard is a plane figure, et cetera, your desktop, the walls or something. The way things work there. Well, you've got 3 equations for problem number 8 for practice exam number 2. You got 3 equations and 3 unknowns. 3 equations and 3 unknowns. Yeah, you can solve it as long as they're linearly independent. As long as they're not, none of them are the same equation with something else that's there. All 3 of them are different from one another. They're different equations. There's no 2 of them are identical equations. So if you got 3 equations and 3 unknowns, or 4 equations and 4 unknowns, if they're all linearly independent, or n equations and n unknowns, you can solve them. N linear equations and n unknowns, you can absolutely solve them. So some beautiful mathematics that pertains to that. For number 8, solving 3 equations and 3 unknowns. You could use matrices and determinants. We're not going to go there. If you're going to do graphing, man, graphing in 3-dimensional space is probably not the easiest thing to do. So, I mean, whatever. I mean, we could kind of look at that. But basically what they're saying is each one of those 3 equations in 3 unknowns, each one of them is a plane figure in 3-dimensional space. All 3 of those planes are flying all over the place in 3-dimensional space, and they intersect one another. They all intersect at one point in 3-dimensional space. X, comma, Y, comma, Z equals, whatever it equals. X equals 2, Y equals 5, Z equals -50, whatever. They intersect at a particular point in 3-dimensional space with coordinates X, comma, Y, comma, Z. For example, if you look at any room you're in, if you look at the corner of the room, look at the floor as a plane, look at the side wall as a plane, and look at the other side wall as a plane, and where they intersect at the very bottom, at the very corner of the room, at the very bottom of the room, where they intersect is one point in 3-dimensional space. Now, those 3 planes are perpendicular to one another. They don't have to be. They can be flying around in so many different directions and still hit at one point. When they hit at one point, you have a unique solution. When they don't hit at one point, you've got to describe things differently. I don't really want to go there right now. I don't think it's very important for us right now to go there. Right now, for the basic stuff that we're doing, given our circumstances, let's leave it at that. They're going to intersect at one unique point in 3-dimensional space. Well, I'm going to show you, it's basically an elimination method to get something like this done in 3-dimensional space. And you could also use determinants and matrices. Not really going to go there right now on this. I think it's just going to use kind of a fancy elimination / substitution method to get a lot of this stuff done. So let's have a look at it. All right, guys, see what we got here. See what we can say. So for problem 8, they go kind of along this line. And again, guys, there's a lot of ways to do problems like this. If you know what you're doing, more power to you. Do the job. But I'll give you an idea I'll give you some ideas of some good ways to do stuff. It's got to work for you. Get it right. Get it right. All right. So you got something like this. You got 3 equations and 3 unknowns. You're probably wondering, yeah, Melis, I don't see the y there for the second equation. If you don't see the y there, kind of make one up. Plus 0 times y, that's always going to be 0. Z is the same as 1z. Z is the same as 1z. X is the same as 1x. X is the same as 1x. Y is the same as 1y. Minus 1y is plus a negative 1y. Generally speaking, you don't have to do what I'm doing. You only have to do one thing. In all the mathematics you ever do in any of my classes, get the right answer. You know that. I think I've already said that. I'm saying it again. I always say it. I mean, get the right answer. Know what you're doing and get the right answer. Wherever there's not a variable there, go 0 times the variable. Give a placeholder there. 0 times that variable is always 0. Whenever there's a letter by itself, put a 1 in front of it. Whenever there's subtraction, make it into addition. That's my advice. That's your business, what you do, but that's my advice. That's a good way to do it. Now you've got the same 3 equations and 3 unknowns. There's some bookkeeping here that we're doing, so let's see what we can say when we're doing this thing. I'm looking at this thing, I'm wondering, okay, how do I want to do it? There are at least 9 different ways to begin this problem. There are at least 9 different ways to begin this problem, let alone how you finish it off. I mean, there's a lot of ways to go here. Typically, what you do is you eliminate repeatedly. You got 3 equations and 3 unknowns. Try to make it 2 equations and 2 unknowns, and then go about the business that you know how to do, that I just showed you how to do, that you already know how to do possibly as well. You're reading the book as well on this stuff. You know how to do this stuff. If you don't know how to do it, you're going to follow what I'm doing. You're going to know how to do it, and you're also going to be reading the book as well. Okay, so we're going to figure this out. You look at this right here. I don't know. I'm going to eliminate one of the letters, and then you always work your way back to get an answer. Here it is. I mean, the big thing is you want the answer's got to be of the form x equals something, y equals something, z equals something. It's going to be x comma y comma z equals, you got me, something here, something there, something there. We got to figure out what that is. But it's right up here is what you're looking at getting. I don't know, I could eliminate the x's and then solve for y's in there. I could eliminate the y's and solve for other stuff. Tell you what I'm going to do. I'm going to take this equation right here. Let me kind of see how I'm going to do it. This one, the y's already not even there. Let me use this guy as a battering ram. I can use any one of these 3 equations as a battering ram to hit the remaining 2. This one right here, 0 times y is just 0. I got 3x plus 1z. 3x plus 1z equals 5. Okay, the y is already out of here. For this guy right here, what do you say you double this guy? You double this guy all the way across. Multiply by 2 all the way across. You got 2x, multiply by 2 all the way across. 2x plus negative 2y plus 10z equals 40. I'm going to leave this guy alone, and you're going to see what I'm about to do. What's staring me in the face? Well, it looks like elimination method is a good way to go here. What do you mean? I mean, just add the stuff. What's 2x and 1x? 3x. What's negative 2y and positive 2y? Nothing. What is 10z and 1z? What is 40 and 15? 55. Let's put him right here. 3x plus 11z equals 55. Equals 55. What is going on here? Well, now I got 2 equations and 2 unknowns. Yeah, Milos, you're trying to solve 3 equations and 3 unknowns. What are you doing? I'm going to work backwards and get everybody. I'm going to work backwards and get everybody. Tell you what, there's an easy way and a hard way, I guess you could say. Right here, man, what's staring at me is I could probably get rid of the x's if I play it right. And then I can just solve for z and kind of work my way backwards. Let me see what I can do here. Let me take the top equation and multiply by -1. That's all you're doing. You're kicking things around. Leave the second equation alone. Here, add them up. Add these two. You got 0. Add these two. Add these two. Really? 10z is equal to 50. Divide by 10 on each side. Z equals 5. For these two guys, like I said, we eliminated as much as we can here related to this stuff, you guys, and we figured out what was going on. There's a lot of mathematics here on this. So we said, okay, that's z is 5. If z is equal to 5, what do you say you come up to one of these two guys? So the big thing here was you found where something could be. You're looking. There's a lot here. There's a lot of discussion. I wish I could get in. I wish we were face to face, guys, talking to one another on this stuff. It's pretty fascinating stuff. But z equals 5. Put z equals 5 right here, or put z equals 5 right here. It doesn't matter. For the heck of it, let's put it right there. 3x plus 11z. You're really doing the elimination method here. You said z equals 5, huh? Okay, z is equal to 5. Okay. Subtract 55 on each side. Divide by 3. X equals 0. Great. X equals 0, z equals 5. Be my guest. We said they all have to have in common. This is very interesting stuff in this regard, I guess you could say. We're looking at this thing, you guys, and I guess the way you want to look at it is, in relation to one another, they're all going to have to work out here. So let's see what we got here. Z equals 5, x equals 0. Be my guest. Use this guy, or this guy to find what y is. Well, I'll tell you what, you can't use this guy. Y is not really in this particular equation. He kind of is fake-wise, but I'm not going to divide by 0 when I solve this thing. So I got to use the other two. It's your call. Let's do this one. What the heck? You got 1x plus 2y plus 1z equals 15. So you got, let's kind of go here. Let's kind of put them in there. And we got x equals 0, z equals 5. X equals 0. Don't know what y is yet. And z equals 5. Equals 15. 1 times 0 is 0. You got 2y plus 1 times 5 is 5 is equal to 15. Subtract 5 on each side. 2y is equal to 10. Divide by 2 on each side. Y is equal to 5. X equals 0. Y equals 5. Z equals 5. X equals 0. Y equals 5. Z equals 5. That's basically the argument to get through the process. Let me just double check it, guys, just in case. Don't want to. It's easier to correct this stuff right now that I am on camera. Yeah, 055. Yeah, you got it. 055. Yep. So there it is. This works. And what the way it works is, you know, you can have the stuff behave as it behaves and find out the ones that would do it, you know, find out how these guys would work in common. Well, you do it in such a way that you find the commonality, and you're assuming that the commonality would also exist. So you find the commonality of two equations, and then you're trying to find it here. Now, this guy, the fact that you're bringing him in here and doing something with him means it's already accounted for, how that actually plays out for you to get the answer. So there's a lot more to this than meets the eye, you guys, and some beautiful math that's pertaining to it. Wish I could talk more about it, you know. But there it is. Pretty important stuff in that regard. As we continue, they talk about like different, you know, they talk about word problems, which are, you know, I guess they're not always the most fun, but see where that is going to be, you guys. Let me kind of see what I want to do here. Okay, so there's some great word problems here, you guys. So let's take a look at it. Let me try to find how exactly I want to go with this stuff, you guys, to get it done. I'm going to do as much as I can. I'm going to try to do the whole exam in one session today. Let's see how that works out. But let's see what we can do. Great problems here, guys. I mean, that we can kind of look at, and some are more challenging, and as such, potentially more enriching than some other ones are, I think. Let's take a look at what we can say. Now, solving these things using linear equations, you guys, all right. They say a couple things here, so let me try to see how I want to do this. Let's look at number 9, for example. Guys, I'm going to kind of try to pick and choose here, be as efficient as I can be while covering a lot of ground for you guys, I hope. Number 9, well, they're saying one number is 7 less than a second number. Twice the second number is 4 less than 5 times the first. Find the two numbers. What's going on here? I'll tell you what. Let's call x the first number. Let's call y the second number. They're saying here one number is 7 less than a second number. One number is 7 less than a second number. So the second number is y. This guy is 7 less than y. So here's one equation for you. Twice the second number, twice the second is means equals. Twice the second number is 4 less than 5 times the first number. It's 4 less than 5 times the first number. Find the two numbers. Okay, here we go. Let's do it again. One number is 7 less than a second number. Twice that second number is 4 less than 5 times the first number. Find the numbers. It's 2 equations and 2 unknowns, you guys. You can do a lot of stuff here. I think the slick way to do it is this. If x equals this, put x right here. 2y equals 5 times x, and x is equal to this. Probably the easiest way to go. -4. So I just substitute this right into here. What's the point? The point is you got to get, you got to have the mathematics work out. And the way the mathematics works out is you got to eliminate what you need to eliminate, and you need one thing by itself. Go for it. 2y is 2y. 5 times y is 5y. 5 times -7 is -35. -4. Let's see. -35 is plus a -35. -4 is plus a -4. You know by now I like to add. Let's subtract 5y on each side. Let's divide by -3 on each side. The old rules, they don't go away. Negative divided by negative is a positive answer. 13. Y equals 13. If y equals 13, what does x equal? Doesn't x equal y -7? If y is, doesn't x equal y -7? Y is 13. 13 minus 7 is 6. X equals 6. Y equals 13. Is it true? Well, yeah, it's true all over the place. I mean, put a 13 right here. Put a 13 right here and -7. Put a 13 right here, -7, you get 6. Y is 13, x is 6. Yeah, that doesn't necessarily mean it works here. But here it does. 13 minus 7 is 6. Here's your 6, here's your 13. Put a 6 right here. 5 times 6, you're claiming it's 6 and 13. 5 times 6 is 30, -4 is 26. 26, huh? 2 times 13 is 26. It works in both equations. It's got to work in both equations. When you solve the system of equations simultaneously, it will work in both equations. Okay? A lot of things you can do here. Let's look at 11. Two cars leave a city and head in the same direction. After 5 hours, the faster car is 15 miles ahead of the slower car. The slower car has traveled 230 miles total. Find the speeds of the two cars. It's a great question here. This is number 11, you guys. How do you want to do this one? Well, let's see. Two cars leave a city and head in the same direction. So they both go in the same direction. They leave the city and they leave the city at the same time and they head in the same direction. They leave at the same time. After 5 hours, the faster car is 5 miles ahead of the slower car. The slower car has traveled 230 miles. Find the speed of the two cars. Now, I want to just kind of argue myself how I want to do this. We'll say that the fast car. There's a number of ways we can go here with this thing, you guys. How we're going to do this. I'd like to say we'll say that R1 equals speed of slow car. R2 equals speed of fast car. Take off at the same time, going in the same direction. They're going at a constant speed. No acceleration here in this instance. R1 equals speed of slow car. R2 equals speed of fast car. Sounds good to me. Tell you what I'm going to do. 5 hours is 5 hours. The slow car went 230 miles. Is it true that distance equals rate times time? Rate of speed times time will give you distance. The slow car went 230 miles. The slow car went 230 miles going at speed R1. 5 miles for 5 hours. After 5 hours, the faster car is 15 miles ahead of the slower car. The slower car has traveled. After 5 hours, the slower car went there. Okay, that's not bad. The faster car has gone 15 miles further. Add 15 onto that. Not too bad. That's pretty straightforward. If you divide by 5 on each side for the top one, you get R1 is going 46 miles per hour. You divide by 5 on this one, it's going 49 miles per hour. Divide by 5 on each side here, it's going 49. And that'd be it. So a little bit easier than we thought we would, but the interpretation of it, once you interpret things correctly sometimes, it makes things a lot easier to look at. Sometimes you can interpret things correctly and they're still very hard to deal with. But we got the speeds right here, looking real good. All right. So these glasses are about the worst thing the worst glasses I ever had. I basically got to glue the thing to my face to do it. I didn't bring my other readers, so dealing with this one. Let's look at a couple of aircraft problems. I think they're pretty interesting. Let's look at problem 12 and problem 14. They look pretty good. Okay. The 12 and I think 12 and 14 will be the way to go on this one. 12 and 14. For 12, they're saying a chemist needs 150 milliliters of a 58% solution, but has only 25% and 70% solutions available. How many milliliters of each that should be mixed to get the desired solution? We're doing this via volume. If the solution was 100% of something, it means by volume. Now you can argue this a whole bunch of ways. I guess you could. I don't want to delve into that. It's not, we're not in a chemistry class, So, but we could be, right? The math is the math. It always works. But the way you can look at a problem like this is say that by volume, if something's 100% of 100%, the solution is 100% pure or whatever it is. It's 100% whatever's in there. 100% of substance X is in there. That's a 100% solution. A 70% solution means 70%, so 100% of the volume is substance X if it's a 100% solution. If it's a 70% solution, 70% of the volume is substance X. The other 30% left over is water that's helping to just have it in there, I guess you could say. If it's 25% substance X, the other 75% is water or something. So I got to mix this up so I get, at the end of the day, a solution that is 58% solution. And you got 150 milliliters. Well, I'll tell you what. There's a number of ways you can do it. We'll say X equals amount in milliliters. X equals amount in milliliters of 25% solution. Y equals amount in milliliters of 70% solution. Sounds good to me. So how are you going to get it? Well, I got to find out what's going on here. What you got to find out is you want 58% of the solution. You want a 58% solution. That means the pure amount of substance A, it's got to be 58% from the volume that's given. 58% of 150 milliliters is going to give you the pure amount. How much pure amount do you have in 150 milliliters? Oh, the pure amount? We'll call it substance A. It's 100% of substance A, 100% solution. That means all 150 milliliters are substance A. If it's a 58% solution, it's 58% times 150. That's pure substance A. Sounds good. Well, let's get that amount of pure substance A by going 25% of amount X plus 70% of amount Y. Okay. Oh, another thing to remember. It's 150 milliliters total. I'm going to put X amount. I'm going to put Y amount. Together, they got to add up to 150. Ladies and gentlemen, you basically got the two equations and two unknowns right here. This guy right here becomes 58% is 0.58 times 150. 25% is 0.25. 70% is 0.70. See what I can do about that. Let me multiply the two. I don't have a calculator on me, so I'll do it in my head. There's a trick to this. It's going to be essentially, if you multiply this by 100, divide that by 100, you got 1.5 times 58. It becomes 58 plus 29. It should be 87, I think is what it comes out to. Let me just kind of confirm that. That should be 87. There's a trick to it. If you move this decimal place over 2 places, make it 100 bigger, and then make this 100 smaller, it becomes 1.5 times 58, which is 58 times 1.5, which is 29 plus 58. Sure, I think it's 87. Not a problem there. So we got this, and we got that. Now, is there, now what? I mean, you can leave it like this, no big deal. And then the other guy is this. You got 150 equals x, which is the same as 1x, plus y, which is the same as 1y. That is it. You can do this a whole bunch of ways because this is solving 2 equations and 2 unknowns. I'd probably use, I think that's kind of jumping out at me right now, is probably using the elimination method on this thing. I'd probably multiply, there's a lot of, I guess there's a lot you can do here. Let's go. Like I said, unfortunately I did not, I maybe could find a calculator in there. If not, we're not going to worry about it. The procedure's the big thing, guys. You know how to solve 2 equations and 2 unknowns, you're going to get the right answer. Period. It'll be as simple as that. Let's see what we can do. Let me multiply by a -4 on the top. If I multiply by a -4 on the top, it's going to be multiply by -4 on the top, you get that right there. Let me add them. Add these two. I get that's 0. I constructed it to be 0. Add right here, I got -1.8 times y. This is negative that. Y equals -198 divided by -1.8. Divide by -1.8 on each side. I think we'll be okay. Trying to put this thing together, guys. It should be on the order of 110. I think we actually do this thing. You actually do the division here. Y is going to be equal to negative divided by negative is positive. I'm saying it's 110 milliliters, which means that x and y have to add up to 150. What is x going to have to be? 40 milliliters. That might be the whole problem solved right there, you guys. Let's take a look at it. I am trying to look at it, make some sense out of it. One way I would probably do this, let me just look at it. Let me look at it really quickly, guys. Negative divided by negative is positive. If I multiply this by 11, just the 1.8 multiplied by 11, I would get 19.8. That's a factor of 10 off of here. Multiply by 10, you get here. You'll get it. That's the right answer. That's definitely the right answer. X equals 40. Yeah, I guess it's gotta be more heavily skewed. It's gotta be more heavily skewed toward the 70%. 25 is pretty small. 70% is closer to where you want to go, so it's probably gonna. This guy doesn't pack too much of a punch. This packs more of a punch, and you're gonna have to go that way to get a high percentage. If you want a low percentage, the X would have to be bigger. But it's pretty fascinating stuff. Does it work? Yeah, I mean 40 and 110 is 150. Yeah, that's easy. How about here? 0.25 times 40. 1/4. 0.25 is 1/4. 1/4 of 40 is 10. 10, huh? All right, that's 10. 0.70 or 0.7 times 110 is 77. 77 and 10 is 87. Right on the mark. Right on the mark, guys. That worked. Let's go to problem number 14. Talk about an aircraft. They're great problems, you guys. Good gut feeling problems as to how this stuff works out. You can see this stuff for you guys wherever you want to go into in life. You want to go into engineering. You want to study physics, like whatever. You take a physics class or already taking a physics class. This is going to help you. Anything you're doing, this is going to help you. You know, for those are my people in the physics class. Those are my students in the physics class. Please, yes, absolutely, use this. Use this. For those that are looking, for those of my students, because we're all on the same team. Wherever I'm going to teach, you guys are all incredibly important. You all have incredible potential. Everybody. I don't care what school you're at, who you are. Don't care. You have incredible potential. Let's work for it. Let's get it. Some of the great mathematics that's here, if we know how to do it, is going to help us reach our potential. Do we want to go into nursing? Do we want to go into physical therapy? Do we want to be medical professionals in the sense of biologists? Or do we want to be doctors, physicians, in other words? Do we want to be engineers or physicists? You name it, guys. Every one of my students, no matter where I've ever taught, has had tremendous potential. You guys can do this. You guys can do great. And I'm looking forward to seeing you do great. It's a great problem. You like problems like this. They tell you a lot. Really puts the mathematics into into a mode where you can apply everything that you want to apply. Let's see what else that we can say. Let's go to problem 14. Okay, same kind of game here, guys, with problem number 14. Can we apply this stuff? Do we know what we're doing? Give me 1 second, guys. All right, excuse me. For number 14, they're saying a certain aircraft can fly 1,400 miles with the wind in 5 hours and traveled the same distance against the wind in 7 hours. What is the speed of the wind? Heck, the way they're talking, guys, well, we can do them one better. We'll not only find the speed of the wind, we'll find the speed of the aircraft, assuming it's a constant speed that we're talking about when we do this stuff. So for 14, you guys, let's see if this marker's going to work. It's about to go, but we can go a little bit. A certain aircraft can fly 1,400 miles with the wind in 5 hours and travel the same distance against the wind. Well, I'll tell you what I'm going to do. I'm going to say R equals the speed of the aircraft in still wind. So some of these markers, guys, it's kind of hit and miss. Forgive me here. I regret having thrown away that first marker, to be honest with you, at this point, right? See how legible that is? Yeah, it's not that good. All right, let's try it again. Yeah. I don't know, guys. Let's try this. Legible. Let's say speed of aircraft in still air. Let's say there's no wind. The one good thing, guys, is I have about 900 markers in here. That's one good thing. The bad thing is I think none of them work. So let's see. So, all right. I get the one marker that actually works. Let's stay with it for a while. They don't last that long, but when they're working good. Okay, so R equals the speed of aircraft in still air. R equals the speed of the aircraft in still air, and W equals speed of wind. It's a lot easier than you think, guys. Let's have a look. Certain aircraft can fly 1,400 miles with the wind in 5 hours. All right, let's see here. You're telling me it's in kind of the back of my mind. The general formula we look at is D equals R times T, right? The rate of speed times time will give you the distance that's traveled, at least in this very basic generic sense that they're talking about. A certain aircraft can fly 1,400 miles with the wind in 5 hours. So it can go 1,400 miles. What's with the wind mean? It means still air plus wind put together times the time of 5 hours. The wind is carrying the airplane, and the airplane is also pushing against the wind that's carrying it. In plain English, R plus W is the speed with the wind. Still air speed is R, wind speed is W. Put them together, it's like me running very fast and I'm on a train. If I'm running at 10 meters per second and the train is going 20 meters per second, the person on the ground sees the train at 20 meters per second and me at 10 meters per second on the train. 20 plus 10 is 30 meters. It looks like I'm going 30 meters per second. Why? Because the train is kind of the wind. the train is carrying me while I'm running on that train. Train going at 20, I'm going at 10, together it's 30. Speed and still air, speed of the wind. It goes the same distance, and it travels the same distance in 7 hours against the wind. Same distance against the wind. That's it. That's it. A lot of ways to go right here, but man, I think they're pretty straightforward stuff. I think probably the easiest way to go is this. Take the top equation, divide by 5 on each side of the top equation, and you got r plus w. Divide by 5, that's 280. Bottom equation, divide by 7 on each side. That's the ticket. That's the way to go. Right there, that's the way to go, I think. Write the top one, write that one right here. R plus W equals 280. The bottom one is R minus W equals 200. Sounds good to me. That's the ticket. Tell you what I'm going to do. A real easy way to go is this. They only ask for the wind speed. Man, what's the point? We can get the speed in still air and we can get the wind speed. It's convenient to do so anyway. Why don't you take these two equations and add them together? R and R is 2R. W and W is 0. Let's try it again. Add these two equations. R and R is 2R. W and negative W is 0. Minus W is the same as negative W. Add these two. Divide by 2. Right? Divide by 2, and you end up getting 240 rather. Those miles they were talking about, let's come back to it. Yeah, they were miles. That's miles per hour. Miles per hour, or mph. That's the speed of the airplane in still air. What's the wind speed? Pretty easy one at that point. Put 240 right here. Put 240 right here. What would you add on to 240 to get 280? 40. 40 mile per hour wind. Yeah, when it's with you, you're getting a lot of help. When it's against you, what's 240 minus 40? It's 200. Either way you plug it in, you can solve it, guys. That's the wind speed, and that's the rate of speed there. So on and so forth. They do a similar argument for problem number 15. If you know how to do one, you know how to do the other. Let's talk about, they talk about something like problem number 16. They're saying, given the cost function, C of x, and the revenue function, R of x, find the number of units x that must be sold to break even. So this thing right here, they say there's a cost function. The more you're making, the more units you're making, the more cost there's going to be. Yeah, that makes sense. I guess I gotta, it costs money to make a lot of units, you guys. So this is the cost function that they're talking about. This is the cost function they're talking about. And the revenue function, well, the more you make, as long as you can sell it, it's you're also going to make more money. Yeah, I mean, to make a lot of money, you got to incur a lot of cost, I guess. To make a lot of money, you got to incur a lot of cost, and maybe there's a break-even point, and maybe there's a point that goes beyond that. This should get real good. You should make a lot of money if you make a lot of stuff. Yeah, if you make a lot of stuff, you'll make a lot of money, provided that you can sell that. Provided that you can sell that stuff. The break-even point, you guys, would be the C of x would have to equal R of x. Remember, C of x would have to equal R of x. So, or R of x equals C of x, whatever, doesn't really matter. The big thing here is So let's put R of x in here. Let's put C of x in here. Why don't you subtract 9,000x on each side? Divide by 8,000 on each side. If you make X units, you break even. If you go beyond X units, provided there's sales being made. Now, I'm not an economist, so I don't know how viable this is, but according to the formulation here, if you go beyond X units, I think you're looking at a situation this thing's going to go beyond that. Let me just look at it to be sure here. Let me kind of take a good look here. Yes, I mean it would go beyond that. Yeah, because if you went beyond that, you make a profit of like 8,000 with one more unit beyond that. If you were to do that, actually, you got the 8 right here. You got the 8 right here. They break even. If you go 9 units here, this is 9,000 more. Yeah, but this is 17,000 more. Beyond the 8 units, you're gonna make profit. Less than the 8 units, you're not gonna make profit. Okay. Again, the mathematics is, regardless of our field of endeavor, guys, the mathematics explains a lot of stuff. The formulations are quite good that we do. You see here what we got. That was 16. Now there's some other stuff that goes on here. Kind of look at it really quickly if you don't mind. Yeah, see exactly how far I want to go with this stuff today. I can know what I don't finish today. I can do the next time with you guys, and we can piece it together, I guess. But let me see what I can do. I mean, I'm somewhat optimistic about it. There's a lot here, but we can definitely do it. There is the idea of polynomials. Polynomials are it's from the Greek word poly and nomos or nomia, onoma probably name. Poly means many, onoma means name, many named expression, many termed expression. There's x to the third plus 9x squared minus 15x plus 20. That's a polynomial. If there's just one item written down, like 9x squared, that's a polynomial known as a monomial. Mono means one by itself, one or by itself. Monomial. If there's two terms like 2x plus 9y, those two terms are called a binomial. A monomial would just be the 2x or 19x to the 15th. That's still a monomial. 19x to the 15th is a monomial, but 19x to the 15th plus 20x is a binomial. 19x to the 15th plus 20x plus 19, that's 3 terms. It's called a trinomial. In general, all of them they call polynomials. Even if it's just one term, they'll call it a polynomial. So we'll deal with polynomials. We'll deal with some aspects of multiplication, division, multiplication and division of polynomials, and factorization of polynomials, and how we can solve certain things. I think it's going to be pretty worthwhile for us. So let's go in that direction. Let me, there's a lot of ways to look at this, guys. Let me at least give you one way each of the times I'm looking at a particular problem. Let me at least give you one way that's strong and that works. But when you read the book and when you read when you read the book or when you do this on your own, you may find something else to be more efficient for you. please go ahead and use that way of doing it, provided that you get the right answer, obviously. Okay. Let's go to problem 19, and we'll take it from there, and then proceed, and I'll look at some of the stuff that I can say here, you guys. I think within the context of doing the problems, I think it should be pretty clear to us how to do certain things. So let's see what we can say and do. Let's start with problem 19 as we move forward. All right, guys, they're saying here, like goes with like, you guys. You do. I've already kind of gone, and I've done this in earlier discussions pertaining to this matter of when you do the distributive property and when you don't do the distributive property, and what you can combine and what you cannot combine. When you're adding or subtracting like terms, you got to have the same tail end of the term associated with each of the terms that you're combining. If it's x to the fourth and x to the third, you can't combine them. You can add them, but you got to leave them alone as is. You've added them. If I had 5 apples and 3 oranges, don't say that I can't add them. Sure I can. I'll put them in a bucket and I've added them. How have I added them? Well, I got 5 apples. I put 5 apples in the bucket and 3 oranges in the bucket. Yeah, there's 8 pieces of fruit. There's not 8 apple oranges though. It's just 5 apples and 3 oranges. I added them. I put them in the bucket, sure. Now, if I got 5 apples and 3 apples, I do have 8 apples. Or if I have 5 oranges and 3 oranges, I do have 8 oranges. But you can only combine like terms to simplify when you're adding or subtracting. They got to be like terms. If they're not like terms, you can't do it. Can't do it. So, I mean, with that in mind, I mean, let's kind of, it should kind of get there. Now, there's ways you can do it. I'll show you the way I would do 19. Again, how you do it is your own business, guys. I'll show you what works. I can't show you everything that works because I don't think anybody's got the time to show you everything that works. But we can show you, I can show you what works, and you kind of use that logic to get the job done. Okay, you're looking at it. Now what are you going to do about it? What I usually do is I make everybody into addition. Watch out for this guy right here. Minus this is plus the opposite. 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 Okay, so far so good. If there's nothing in front of it, put a 1 in front of it. If there's nothing in front of this guy, put a 1 in front of it. Then I take the minus all this, minus all of this is plus the opposite of all that. If you take the 1 and distribute it, well, it's pretty easy. It's rather trivial. You get 5x to the 7th plus negative 5x to the 5th plus negative 6. Watch out. Be careful. Let's go. Negative 1. Well, let's just do it. Negative 1 times positive 8x to the 7th. Negative 1 times negative 10 is positive 10. Bring that along. Negative 1 times negative 16 is positive 16. I'm going to take the 7s and put them together. I'm going to take the x to the 7ths and put them together. I'm going to take the x to the 5ths and put them together. Now I'm going to take regular numbers and put them together. And like goes with like when you do this. 5x to the 7th and negative 8x to the 7th is negative 3x to the 7th. You don't get more exponent. If I add, if I have a bunch of boxes that are called x to the 7, when I add a bunch of them together, they're the same kind of box, there's just more of them. The boxes don't change, the number of boxes change. So the exponent, the exponentiated quantities don't change. Said that last time. I said that last time. 5x to the 7th and negative 8. 5x to the 7th and negative 8x to the 7th is negative 3x to the 7th. Negative 5x to the 5th and positive 10x to the 5th is 5x to the 5th. 6 and 16 is 22. And there it is. And there it is. That'd be 19. They're doing stuff like this all over the place, guys. I mean, you kind of, let's see exactly how I want to do this. For problem 20, for example, here you will do the distributive principle, and you got to be careful. They're giving us this. They're giving us this. And I'm going to say this right off the bat. I like that. You don't have to do whatever you want. If you get this right, you get it right. I've said that. Again, I wish I was with you guys in person. It's the best way to teach. I've been saying that forever. And I guess we see that now with this crisis, that every teacher sees that. Your best being right there with your students, But here, let's do what we can. I mean, so what we're looking at here is minus 3y. Minus 3y is plus a negative 3y. I like to add. There we go. You will not distribute again because there's no addition in here. I know there's addition right there. We know that. That's why I know there's addition right there. That's why we distributed it in the first place. But you don't do it again. We've said that. Like goes with like. 5 times negative 10, negative 50. X times x. Negative 3 times negative 10, positive 30. X is x, y times y, y squared. These are not like terms. I know there's x's and y's. I know there's a 2 right here as an exponent. I get it. The exponent has to be in the same corresponding place as it is somewhere else. Same letters, same exact exponents, and all exponentiation has to be in the same place in all instances for there to be common terms. These are not common terms. You're not going to add these any more than what they are right now. Get it down to here. We've gone into this a bit. I mean, we've seen some of this. That's fine. I mean, that's fine. So what? We can keep going and keep looking at it. That's good too. So you're looking at stuff like this, you guys. There's something like problem number 22. You got 2x plus 11, 3x minus 10. Minus 10 is plus the opposite of 10. What did I do last time? What did I do a while ago? You will distribute twice. You'll take the 2x right here and bring it to these two guys right there. Then you'll take the 11 and bring it to those two guys as well. And you're done. That's how it proceeds. So you look at it, you say, okay, what did he just say? Well, this is exactly what I just said. You're doing this. The FOIL method, ladies and gentlemen, the FOIL method is simply the distributive principle applied twice. It's simply a rip-off of the distributive principle. It is the distributive principle applied twice. So you look at it. Let's see what we got here. Go 2x. Go 2x times 3x. Go 2x times negative 10. You distributed the 2x. Now distribute the 11. Now distribute the 11. Keep distributing the 11. What's going on here? You're not going to distribute again. You got them separated like this. Yeah, I get that. But that multiplication's got no addition or subtraction inside of it. Nor does that, nor does this, nor does that. Between them, there's addition and subtraction. I get that. Two times 3. X times x. Let's try it again. 2 times 3, 6. X times x squared. Negative 10 times 2, you're not distributing. Just go negative 10 times 2 and you're done. And then tack on the x. Here you go 11 times 3 and then tack on the x. Here you go 11 times negative 10. Well, that and that got nothing to be put together with. But this does. And that does. You got 6x squared plus negative 21 apples and 33 apples is not as many apples, but they're still apples. You don't get squares here. That's minus 110 or plus a negative 110. I don't think it's going to be an issue. Depends how they ask you to give the how they want you to give the answer and stuff. But they got answer blanks and stuff like that. There's a lot to look at depending on the system that's being employed. So 6x squared plus 13x plus negative 110. Yeah, looks pretty good. That's 22, you guys. 24, they're pulling basically the same thing. There's no short. And again, this is kind of coming back to the do's and don'ts. Look at this. This looks a lot like the do's and don'ts that we were talking about the last time that we were together, you guys. So let's see what we can do. All right, guys, look at like a problem like 24. Not much of a big difference, guys. Stuff we've been doing. 10m minus n, the whole thing squared. Again, we're not going to bring that square in there and hit at each item and then say we're done. Remember, that's part of the do's and don'ts that we were talking about a little bit of time ago, right? We were talking about in another discussion. We talked about some of the do's and don'ts. You can't do that. What you're looking at this right here. So you got it right here. So what is this? Well, I can't bring the square inside like that. So what can I do? How about just write it like this? That's how you're going to write it. And the rest you're going to FOIL it out. That's all it is. This is FOIL method at that point. N is the same as 1n. N is the same as 1n. Plus a negative 1, plus a negative 1. You don't have to do that, but I'm doing it. Take this guy, go here. Take this guy, go there. Same thing here. Take this guy. Go here, go here. What do we got? And this, like I said, later on, guys, we're going to do this in our heads. You know, we're going to do it in our heads. Right now, let's kind of take our time a little bit. 10m, 10m. Negative 1n. Again, this is basically the argument, guys, how you're proceeding with this whole process. Let's see what we got here. 10m times 10m. 100m squared. Numbers with numbers, letters with letters. 10m times negative 1n is negative 10mn. Do this right here, it's the same thing. They don't cancel out. Negative and another negative is even more negative. Negative times negative is positive. What's going on here? What's the end of the day on this thing? Every other marker's garbage, you guys. I'm sorry. Let me see. I'll try to read for a little bit. Negative and negative is even more negative. You got a common term. Yeah, that's the only way you're going to add them. Well, that's the only way you're going to add them and have them reduce. That's the thing. That's the answer. See how that looks? It looks okay. I can see it okay here. I hope you guys can see it. Trying for the black markers more than anything, I think. Okay. That's some of the argument that's taking place, you guys. There are a lot you can say here. Like I said, you've already seen me pull this off, you guys. Let's do problem number 26. Let's see problem number 26, you guys. Take a look at it. They're saying this. Again, we've killed a few birds with, we've killed a bunch of birds with just a few stones earlier on, I guess you could say, and we're kind of just repeating some of the stuff that we've done. We've been here. We've already done this. But what the heck? Let's do it anyway. Minus 1 is plus a negative 1. Minus 7x is plus a negative 7x. Take this guy and go here, and go there. Take this guy, go here, and go here. 7x times x squared, or 1x squared if you wish, is that. Rather, 9x times 1x squared. 9x times negative 1 times 1x squared. You'll see why I'm kind of staggering this. You got negative 1 times negative 7x. And you got negative 1 times 1. Nine times 1 is 9. X times x squared is x to the third. 9x times negative 7x is negative 63 x squared. 9x times 1 is 9x. Let's keep going, I guess. Where to go here? Go right here. Let me just make sure I did it right. Looking good, looking pretty good. Negative 1 times 1x squared. Negative 1 times negative 7x. And negative 1 times positive 1. This stuff is, I guess, easier done than talked about sometimes, but again, it's the distributive principle. Guys, I could have 100 items added together here and 1,000 items added together there, and I would do distributive property over and over. How much? How long? How long? If I had 1,000 items, if I had 1,000 terms added together, if I had 1,000 terms added together here, going all the way across the campus, each one of those 1,000 terms would have to distribute, or, you know, if the 1,000 terms here and there was like 100,000 terms here, each one of these 1,000 terms would hit each one of these 100,000 terms. Yeah, I mean, it'd be literally, if you had to do something like that, you know, whatever, I'm trying to get too crazy with the whole process here, but if you had 1,000 terms here multiplied with 100,000 terms there, each one of those 1,000 terms to the left would hit each one of those 100,000 terms. Doing that, you'd have 100 million terms to deal with, and you'd have to put them together. And that's its own process, you know. How many different things you have there. That's something else. Pretty fascinating stuff. Let's add them together. 9x to the third. X to the third is by itself. X squared and x squared, negative 63, and negative 1 is negative 64. 9x, let's see here, 9x and 7x is 16x. Negative 1 times positive 1, okay, we already said that. It's all that. They've got this thing called factorization. Kind of a neat thing. I mean, it's kind of, let me kind of talk about it a little bit. This is the answer, period. You're done. This is the answer. You're done. For the record, if you took the 9x plus negative 1 and multiplied it by the 1x squared plus negative 7x plus 1, well, we did just that, actually. If they gave you this, you could factor it and make it look like that. How easy would that be? Well, it's not that easy. It wouldn't be that easy. Tell you what, if you took this guy, this big thing up here, this whole big thing right here, if you took this whole big thing right here, and you divided it, by 9x plus a -1, you'd get that for an answer, that guy right there. Let's try it actually. It's called long division. Let me talk about some of this stuff. So let's see what we can say regarding some of this stuff, you guys. You kind of remember what we just did. I want to kind of use this to kind of make a point, I guess you could say. So let's see what we can do. Okay, we'll leave that up there. This, if you multiply these two, if you multiply these two, you get that. If you were to take that guy and divide it by this guy, you'd get him. If that makes any sense. Do a little bit of long division with you. See what's going on here, guys. Interesting topic in its own right. Look at it. Basically, they're saying this. Pretty fascinating stuff, if you ask me. I mean, you got this. We got that. Where'd it come from? Came from this. Yeah, it's a true story. We demonstrated it, we did it. This is like capital A, this is like capital B, this whole thing's like capital C. If something's in parentheses, you guys, you can divide a whole chunk of it. That right there, 1x squared plus negative 7x plus 1 is equal to this whole thing. Whole thing divided by 9x plus a negative 1. Yeah, that's the statement. That's the statement being made, you guys. What does that mean? Well, if you did long division, you'd see what I mean. If we took this divided by that, let's kind of, somebody said to you, let's say, let me write it. Okay. This is not the best marker sometimes, guys, as I've already said. 9x to the third, rather, sorry. Nine x to the third minus 64x squared plus 16x minus 1. Let's say they were dividing it by 9x minus 1. Let's see what I can do with it. Let's see what we can do with it. Now, you already know the answer. It's kind of a trick question in a sense, right? You know the answer because the answer is at the end of grinding all this out, you guys. We're going to have 1x squared minus 7x plus 1. 1x squared minus 7x plus 1 or plus a negative 7x plus 1. Tell you what, I'd like to see if that's true. Minus 64 is plus a negative 64. Minus 1 is plus a negative 1. Minus 1 here is plus a negative 1. Okay, now you got to be careful. You take one large chunk right here, the 9x, ignore this guy for now and get him into 9x to the third. 9 goes into 9 one time, x goes into x to the third, x squared times. X squared or 1x squared. Then take the 1x squared and multiply it with both of these two and put it underneath here. 1x squared times 9x is 9x cubed. Well, we knew that because we got the 9x into here to get the 1x squared. Then the 1x squared times negative 1 is negative 1x squared. Okay. Now, take this quantity, subtract it from up there. The minus comes inside, and it becomes negative 9x squared, and 9x squared is 0. Minus a minus is plus 1x squared, and negative 64x squared is negative 63x squared. Then you bring the 16x down. Now take the lead term and get them into this lead term. Go big into big. Lead term into lead term. How many times does 9 go into negative 63? How about negative 7 times? How many times does x go into x squared? How about x times? Now take this negative 7x and multiply it by both of these guys. With both. Get both in there. Negative 7x times 9x is negative 63x squared. Negative 7x times negative 1 is plus 7x. Then subtract all this from there. Bring the minus inside and it hits everybody. Minus a minus is plus. Plus 63x squared and negative 63x squared is 0. Minus 7x and positive 16x is 11x. Forgive me, not 11x. Let's try that again. It should be 9x. What am I talking about? Minus a minus is plus. Plus 63x squared and negative 63x squared is 0. Minus here is negative 7x. Negative 7x and positive 16x is 9x. Now bring a negative 1 down here. Look at it. You can do a whole bunch of stuff here if you want. How many times does 9x go into 9x? How about one time? 1 times all this now. 1 times 9x is 9x. 1 times negative 1 is negative 1. Ladies and gentlemen, these are the same thing. This, subtract the same thing. Negative 9x and positive 9x, 0. Negative of a negative positive. Positive 1 and negative 1, 0. Right here. Did we say that was going to be the case? My marker started to die here, but you can see, you should be able to see it okay. 1x squared plus negative 7x plus 1. That's how you do long division. That's how you do long division. I kind of made that one up, but they should have, and that's the same procedure you're going to do here. When they got, for example, they're saying for 27. See if we can got the same argument here on this whole thing under control. 27. They're saying negative 20 x to the third minus 28x squared plus 7x plus 7. divided by 5x plus 2. They want to see an answer there. I want to see an answer. Let's do what we just did. Let me write this guy, negative 20, x to the third minus 28, x squared, plus 7x, plus 7, five x plus 2 right here. Yeah, that's all they're asking. That's all that they're asking, guys, when they do something like this. See the procedure. Let's follow the procedure. Let's get there. So they're asking, can we do it? Yeah, we can do it. We certainly can do it. We did it before. Minus 28x squared is plus a negative 28x squared. 5x goes into negative 20x to the third. Well, 5 goes into negative 20. 5 goes into negative 20, negative 4 times. X goes into x to the third. Here's x to the third. Here's x. Then we subtract exponents. 3 minus 1 goes in x to the 2. I can take this guy and hit everybody. Hit both of them now. Negative 4x squared times 5x is negative 20x to the third. Negative 4x squared times 2 is negative 8x squared. Let's subtract that whole quantity. Bring the negative inside. Negative of a negative is positive 20x squared. Positive 20x squared and negative 20x squared is 0. Negative of a negative is positive. Positive 8x squared and negative 28x squared. Positive 8x squared and negative 28x squared is negative 20x squared. Bring a 7x down and see if you can go. 5x goes into negative. Go lead term into lead term. 5x into negative 20x squared. 5 goes into negative 20, negative 4 times. 5 goes into negative 20, negative 4 times. X goes into x squared, x times. Now take this guy, negative 4x, and multiply it by both of these. Negative 4x times 5x is negative 20x squared. Yeah, we knew that. We got it from before. Negative 4x times 2 is negative 8x. Subtract. Minus a negative is plus. Minus a minus plus 20x squared. Positive 20x squared and negative 20x squared is 0. Minus a minus is plus, so plus 8x and plus 7x, 15x. Bring a 7 down. Bring a 7 down. Let's see if we can get the lead term to go in here, guys. 5x goes into 15x 3 times. Now this is going to be kind of interesting. 3 times both of those. 15x, 6. When you do the subtraction, 15x minus 15x, 0. 7 minus 6 is 1. There's a remainder of 1. Now let's see how they answered it. The best way to, there's a good way and a bad way to answer this. I mean, well, it's debatable how you want to answer this, but yeah, the remainder of 1. You do the subtraction here, you got 1 left over. You can't go any further, so here's what you got to do. You got a 1 left over, so you go, let's put all of this now. 5x minus 2, let's put it into 1. How many times it go in there? 1 divided by 5x plus 2. Yeah, it's a little messy, but that's how they want to do it. Whenever you got a remainder, the last thing you got. Now, what does this mean? I'll tell you what it means. If you were to take the guy doing the dividing, the divisor, and multiply it with the quotient, and you multiplied it with this guy, 4x squared plus negative 4x plus 3 plus 1 over 5x plus 2. If you were to do this, I think we can get rid of this one. We've already seen it. There it is. If you were to take the 5x plus 2, the divisor, and multiply it with the quotient, negative 4x squared, negative 4x plus 3 plus 1 over 5x plus 2. If you were to distribute the 5x all the way across here, even under this guy, and get 5x over 5x plus 2, and then and then when you're all done with that, distribute the 2 all the way across here, including over here, and get 2 over 5x plus 2. Well, 5x over 5x plus 2 and 2 over 5x plus 2 is 5x plus 2 over 5x plus 2 is 1. 1 and 3 is 4. Well, whatever, you get more than that. But I mean, because you get 1. And the 1 you'd add on to the 6 to get the 7 right here. If you're following me, great. If not, don't lose a whole lot of sleep on it. The big thing I want to tell you is this thing right here is definitely equal to this. They're definitely equal to each other. This, of course, you do the division. So, pretty interesting stuff, you guys. Pretty interesting stuff. They go into the, so that's things we can look at for long division, I guess. Give you some of the argument that precedes that we do to get there. Right, negative 4x squared minus 4x plus 3. So where was it? Right there. Negative 4x squared minus 4x plus 3 plus 1 over 5x plus 2. Neat stuff. Plus a negative is fine too. That's not going to be an issue. So they talk about stuff, how things get factored out, and how you would actually get to certain answers regarding this stuff. So let me see here. Where I can go here, guys, what we can say here. Let me write some things down there. They're kind of like the standards, and we kind of use them to get around stuff when you want to do. I'll make a long story short. This guy, when factored out, comes out to here. This guy, when divided by that, gives you this guy. This top guy right here, this top far right guy. If you take this and divide it by that, you get this guy. You multiply the two, you get this. Kind of takes us into factorization a little bit. So let's see what we can say. Okay. Well, guys, there's some stuff we got to look at, I guess you'd say. There's some tricks of the trade, you guys. There's things we can do, and I think you guys have kind of seen me go there a little bit in earlier discussions that we've done. So what we're going to do is say a couple things here. If you know how to do one, you know how to do the other. If you had something like the quantity a plus b squared, when you grind it out with the FOIL method, it's generally going to look like this. And when you got the quantity a minus b squared and you grind it out, it's generally going to look like this. And if you ever had the quantity a minus b times the quantity a plus b, that comes out to a squared minus b squared, the difference of two squares. If you have a cubed plus b cubed, that factors out like this. And if you've got a cubed minus b cubed, that factors out like this. You can't break this further. It's not looking like this. You can factor it. This stuff, this argument, this presentation cuts both ways. What do I mean? I mean, if you're going to do multiplication, you get an answer. If you get an answer, you can go backwards and make it look like, you know, if I were to say to you multiply, good, here, evaluate this and I get an answer. Then I were to say to you, take this answer and factor it. If you factor it, you get back to there. For all of these, it works that way. If you do the multiplication, if you multiply this stuff out, you get this. If I say, please factor this, here it is factored. So on and so forth. We do some of that stuff. So they say some of that. You got to kind of you got to try to find who plays what role in a particular problem. And it usually, a lot of times, they're going to ask you in a course like this. Not always. It could be a little more complicated. You saw me do the long division, and that didn't fit under any scheme other than, hey, man, I better know how to do long division. I better know how to do long division. I should be okay. For this right here, for example, I mean, there's a lot of looks you can give it here. Let's say you have problem like number 31. Problem 31 is 81x squared minus 64. I'd like to break it up. Well, I'll tell you what. I'm going to take that. I'm going to factor that out. They want me to factor it. I'm going to use this guy. I'm going to use this guy. Why would I use that guy? Well, I already know that a minus b, the quantity a minus b times the quantity a plus b is a squared minus b squared. Okay, sure, yeah, so what? Big deal. Well, I'll tell you what. 81x squared is the same as 9x, the quantity squared. 64 is the same as the quantity 8 squared. Guys, do you see something going on here? I guess this 9x looks a lot like a. I guess this b looks a lot like a. What does that mean? Well, that means a minus b, the quantity a minus b, times the quantity a plus b. If you FOIL this out, ladies and gentlemen, I promise you're going to get this. I promise you're going to get that. For, again, it's kind of a horse apiece on this one, you guys. 33. They talk about this. And they'd like you to break it up into something. Get a factorization. Tell you what I'm going to do. Isn't it true you got A plus B yeah, you're saying that. Can I do it? Yeah, maybe I can. X looks a lot like A. A cubed is a lot like X cubed. B cubed, huh? How about the number 9? Taken to the third power. 9 times 9 is 81. Times 9 is 729. Okay, that works. X looks like A, and 9 looks like B. X looks like A, 9 looks like B, X looks like A, that's 9x. B is 9, square it, you get 81. That's it. X plus 9, x squared plus 9x plus 81. And that's how the factorization goes. Yeah, they do different things here. I think I've seen a couple of these that worked out pretty good. Some of these other problems are coming up here. Let's look at it. Let me do a problem like number 35. Let me erase this, get a clean slate on this thing. We'll take it from there. Take a problem number 35. Okay. See some other stuff we can talk about. Let's say somebody said this to you. I want you to solve this. Now, we got to talk a little bit about some of the stuff here. If you ever see if I can do it. Let me just write this down. Here you go. There's an equation. They'd like you to solve it. Solve for x. A lot of times you're not going to get just one solution for x. The degree of the polynomial tells you the number of solutions that are present. The great mathematician Gauss, Carl Friedrich Gauss, essentially proved that the order of the polynomial will tell you how many solutions you have. I mean, I think the way that the proof's called the fundamental theorem of algebra, he proved something, it was something different than that. It's somewhat different than that, but not recalling right now. It's along those lines. One of the conclusions that are drawn from what he proved is essentially that. You got to introduce this thing called complex numbers for that to be valid. I don't want to clutter things too much. I don't really clutter, it's a fact. But we'll talk more on these matters as time proceeds. But for our purposes, if you got x to the, we're still okay, right? I'm still okay going on this, right? Looks okay. All right. If we have some polynomial like x to the fifth plus negative 5x to the third plus 9 equals 0, the highest power is the degree of the polynomial. X to the fifth, oh, the fifth power is the highest power. There are 5 solutions if you bring in complex numbers. There are 5 solutions. They could be repeat solutions, it could be a double solution, but there's as many solutions as the order of the polynomial. So don't be surprised here if I get an answer that's bigger, or if I get an answer here that's more than just one value of x. You know, the degree of the polynomial will tell you that. Okay. Well, this is a difference of 2 squares. If you grind it out, it's x squared minus 36. If you grind this out, it's x squared minus 36. If you take the 13 and multiply across, correct? You get this. If you get everybody over to the other side, add a negative 13x on each side, add a negative 104 on each side, you end up getting x squared minus 13x. So I'm going to add a negative 13x on each side. I'm going to add a negative 104 on each side. Negative 104 and negative 36, that's plus a negative 36. Negative 36 and negative 104 is negative 140. Is equal to 0. This is a degree 2 polynomial. There will be 2 solutions. If that exponent on top right here was, if it was to the 12th, there'd be 12 solutions. You could have multiple solutions kind of repeating themselves, but according to Gauss, the degree of the polynomial tells you how many solutions that you have. You're allowed to have a double solution or triple solution or whatever, but I want to talk to you. This is a degree 2 polynomial. It's called the quadratic equation. The solution to the quadratic equation can be done either through, and we're going to get into this in another discussion. Somewhere else in another discussion we'll get into this. I don't think I do it on this particular practice exam, but next time we see it, we will see it. But since we'll see it now, we don't have to go too crazy about it the next time we see it. We'll have seen it. This is a degree 2 polynomial and has 2 solutions. How would you solve it? You can do it by factorization. You can do it by factorization, or you can do it by the quadratic formula. If you have a constant a times x squared plus a constant b, these are real a, I'll talk to you about it in a second. And you set it equal to 0, where a, b, and c are any real numbers. Where a, b, and c are any real numbers. If ax squared plus bx plus c equals 0, and you want to solve for x is equal to the opposite of b plus or minus guarantees 2 different solutions. The opposite of b plus or minus the square root of the quantity b squared minus 4ac, the whole thing over 2a. This plus or minus guarantees 2 solutions. This plus or minus guarantees 2 solutions. They could be a double solution, a repeat. The answer could be 2 and then 2 again. That's okay. But this plus or minus guarantees 2 solutions. This is called the quadratic function. And we'll see this again. I mean, we'll see this again, how you work. This is the solution to the quadratic equation. The quadratic function, we set that equal fx equals ax squared plus bx plus c. Okay. I got to talk to you a little bit. They always want things to be written in terms of addition. Now, there's a number of ways to go here. I'm going to go plus a negative 13x right here. Now, I want to talk to you about this. I want to talk to you about it a little bit. X squared is the same as 1x squared. If that were the case, ladies and gentlemen, we got ax squared plus bx plus c equals 0. So I'm kind of jumping the gun on this thing a little bit, but you got to know this stuff eventually anyway, so let's jump the gun. We have the 1 and the b, the the 1 and the a, the negative 13 and the b, and the negative the negative 140 and the C. So basically they're saying here, you could have A, you got to set it in terms of addition now. A equals 1, B equals negative 13, and C equals negative 140. C equals negative 140. So, okay, big deal. Now what, Jim? What are you going to do? Well, I got X here. The opposite of B is the opposite of negative 13. Four. A is 1. C is what? Negative 140. That's pretty big. Where's that going? 2 times A. Okay, that plus or minus is going to get me somewhere, but let's see where it does get me, I guess. The opposite, let's evaluate it. The opposite of negative 13 is 13. Let's go with the plus scenario. The plus scenario is if you take this guy, he's 169. The quantity negative 13 squared. Always put the quantities in brackets or parentheses so you don't do something careless. This is negative this minus all this. 4 times 1 times negative 140 is negative 560. Minus a negative 560 is plus 560. Divided by 2. The bottom guy is 13 minus the same monkey business here. I wrote this horribly, guys, but okay, let me... What is going on here? So let's make sure everything is okay, you guys. Did we do this right? Let me just make sure we got it right here. Uh, 629. For some reason, it's got to be a better answer than that, guys. I gotta. For some reason, guys, let me just make sure we are okay. Negative plus negative 13, you got it. That right there, got it. Four times that. For some reason, guys, I'm just trying to figure out. That's 6. Oh, yeah, it is. It's right. It's fine. It should be fine. Forgive me on that. We got 13 here. I don't know why I blanked out on that one, man. 600 is going to be 729. 729. We encountered that number earlier, if you remember. And we got this. And here we got 13 minus the square root of 729. Now this is not the easiest way to go. Sometimes just do a fact. We're going to get into a factorization. You're going to see what I'm talking about in a second when we do this. The square root. The square root of 729 is 27. So what we get here is we've got 13 plus 27 divided by 2. 13 plus 27 is 40, divided by 2 is 20. Okay, there's an answer for you. Here, it's 13 minus 27. That's negative 14 divided by 2. That's negative 7. I told you it was a degree 2 polynomial. There'd be 2 answers. And this, like I said, when I get into the stuff later on, we're not going to need to do this because we're doing it now. We can we look at it, it's not going to bother us quite as much. X equals 20 is an answer, and x equals -7 is an answer. Each one are answers. You put them in their entirety separately. Is that true? Yeah, I think it is true. Watch. Put a 20 right here. 20 and 8 is 28. 28 times 13 is 364. 28 times 13 is 364. 26, 20 and 6 is 26. 20 minus 6 is 14. 14 times 26 is 364. 364 equals 364 if you put a 20 inside for x. Put a -7 here. -7, and now the 20 works. 364 equals 364. And you put a 20 here, a 20 here, and a 20 here. Absolutely. It was 14 times 26. Absolutely. 364. 364 and 364 are equal to each other. Put a -7 here, -7 here, -7 here. See what happens. -7 and 8 is 1. 1 times 13 is 13. Okay? 1 times 13 is 13. -7 minus 6 is -13. -7 plus 6 is -1. -1 times -13 is 13. 13 equals 13. It works. It works. Very important. Absolutely it works. There's your answer. This is the quadratic equation. When there's a quadratic equation present, and you really draw a blank, the quadratic formula will always get you through. So I wanted to show you that. Now, could I have done it through factorization without worrying about the quadratic formula? Yeah, I mean, you saw what I did. You saw what we got. We're not going to debate it. We got it. We know what we're doing. Let's get the same answers. 20 and -7. Let's do it with factorization. You need to find the 2 binomials, the 2 quantities that you multiply together to make this thing a reality. Well, I do have a question for you. I need to make it equal to 0. You've got to take, okay, this doesn't work. I was having good luck for a second there, guys, with this stuff. Let's try it again. You got to take x squared minus 13x minus 140, set it equal to 0. I gotta let you know something, man. If I get a whole bunch of terms, if I got A, B, C type A, B, C, D, if I got A times B times C times D, and I set it equal to 0, either A's got to be 0, or B's got to be 0, or C's got to be 0, or D's got to be equal to 0. One of them's got to be 0, or all of them, or some combination of them, but at least one of them has to be 0. At least one of them has to be 0. I gotta talk to you. Let me see if we can pull this thing off. Can I make it a binomial times? I gotta make them equal to 0. I'll tell you what I'm gonna do. Is x times x x squared? Is 1 times 140 140? Yeah, we know that. 2 times 70 is 140. 14 times 10 is 140. 20 times 7 is 140. Since we don't have a lot of time, let's pretend I guessed it. You got to do a lot of guessing, and then you multiply it out to get an answer. Why would I take 7 and 20? Because 20 minus 7 is 13. You got to make it somehow work out. In other words, you see, there's a trick to it. You say, okay, let me make that negative, let me make that positive, let me just see it, let me just test it. Always go the outskirts first. If you FOIL this out, would you get that? That's the question. If you FOIL this, if you do the FOIL method here, will you get the thing above it? Answer is yes. You may have to test it 5 different times. But here's how you do it. You go x times x, x squared. 7 times negative 20, negative 140. 7x and negative 20x is negative 13x. It would all add up right. So you'd have to grind. I'll leave you to grind that out. Actually do the FOIL method and see if that gets. You might have to guess a bunch of times. You may have to go 1 times 140, 2 times 70, 14 times 10. Then I go 7 times 20 or 20. That wouldn't work. Because if you add the two or subtract them, what's 20 minus 7? Well, it gives me the middle one. Those two, these two outskirts, you want it to be something associated with 13 when we test it. Okay. So we got this. It works. I got a question for you. Didn't we say this works if this is equal to 0? If x plus 7 equals 0, it works. If x minus 20 equals 0, it works. What number plus 7 gives you 0? X equals negative 7. That looks familiar. What number, subtract 20 from it, gives you 0? X equals 20. Wait a minute, ladies and gentlemen. When we did it the long way, didn't we find that x was equal to 7 and x was equal to 20? So that would solve it also. That would solve it also. A lot of stuff, guys. A lot of stuff. We got it on film. You can always go back and look at it. You're looking at the book as well, and we're going to figure this out. I'm going to try to be as reasonable as I can be with the people who are taking my math class. So we'll try to be reasonable as possible. Generally, guys, this is not, obviously the circumstances are less than ideal. There is another problem that's pretty interesting, and we kind of work with that as well. And this stuff, like I said, it's useful a lot of places. It's useful in physics, chemistry, engineering, anywhere where there's mathematics, guys. If you got the basic mathematics under control, it gives you a stepping stone to go into higher mathematics. You're never going to lose with this stuff, regardless of what you're interested in, what class you're taking. If it's something involving modern technological science, this stuff is worthwhile. It's worthwhile. That's why I'm going to give it kind of a broad expanse of location to a broad number of people. I'm trying to expose people to this sort of stuff. Okay. I hope it works out for everyone. Okay. All right, guys, you talked about the domain of a function. A function is a mapping from one place to another. If I put in, for example, let's look at 37. If they're saying a function f of x means if you plug in a value of x, and grind this whole thing out, you plug in a value of x and you grind this whole thing out, you will get you'll get values. You'll get a value for the function of x depending upon what value the value of f of x is dependent upon the value of x that you put in there. That's a function. The domain of the function the domain of the function means what values of x can you plug in there and still have a valid conclusion to your function. What does that mean? It means what are the values of x that work? What values of x can you put in there and the function actually is valid? You get a valid answer for the function. The easiest way to do that sometimes is finding out what doesn't work. Oftentimes there's an infinite number of values that are part of the domain. There are a few things that don't work, so find out what doesn't work and go there. Every real number in the universe of real numbers on the number line will work in here and give you a valid answer for the function, except for the values of x that would make the bottom thing equal to 0. Because the bottom thing equal to 0 means you're dividing by 0, and that's not defined. All real numbers, the domain here, the domain is the set of all x such that x is an element of the real numbers, but x is not equal to, there's probably going to be two things they're not equal to. This thing right here cannot be equal to 0. We can use the quadratic 0. If that thing's equal to 0, we're in trouble. Let's find out where it's equal to 0. What do you say we do the quadratic equation? You can if you wish. Perhaps you can just factor and it's easier. It might be easier to do the quadratic equation. Let me see what I got here. I can go here, instead of equal to 0. X times x is x squared. 56, huh? 1 times 56 is 56. 2 times 28 is 56. 7 times 8 is 56, and that's probably a winner. What's 7 and 8 when you add them together? You get 15. The middle thing's got 15. I need a negative 15 though. How about a negative 7 plus a negative 8, and then a negative 7 times a negative 8 is 56, right on the mark. X is equal to 7, and x is equal to 8. Solves it. If this is equal to 0, x has to be equal to 7. If this is equal to 0, x has to be equal to 8. You are not allowed to have x equal to 7, nor are you allowed to have x equal 8. Why is that? It is that because if you do got 7 or 8, it's going to be 0 on the bottom. You can't have division by 0. You cannot have division by 0. That's some of what they're talking about there. Talking about writing the rational expression in the lowest terms. Let's do number 39. You cannot, okay, this is a pretty important point. For 39, if you have 3x squared plus 12x over 5x squared plus 23x, and I don't want to get into too much. There's a lot you can say here. We're going to keep it the way they got it kept. They want you to take the rational expression and reduce it to lowest terms. Write this rational expression in lowest terms. What's a rational expression to begin with? Didn't we write down rational numbers earlier? Rational is from the word ratio, a ratio of two expressions. There's an expression on top and there's an expression on the bottom, and you're doing a ratio of the two. Anytime you're doing division, there's a ratio. So much of mathematics is about ratios, whether they tell you that or not. Whether they tell you that or not. Let's see what I can do. Let me factor out as much as I can and see what I can say. This 5x squared plus 23x, I wonder if I could break this thing up. Let me see if I can do a factorization here. How about 5 times x? 5 times x times x is 5x squared. Okay, good for me, good. I got to get 23 in the middle. 28 can break up as 1 times 28, 2 times 14, and 4 times 7. If I put a 4 here and a 7 here, the middle stuff doesn't work out, guys. That smiley face there. 7x and 4 times 5x. 4 times 5x is 20x. 7x is 7x. 7x and 20x is 27x. If it was 27x right here, that's what I'd do. That's what I would do. I can't do it. That's not what they're asking. So I got to find somebody else that gets me to 23. If it was 27 right here, I'm in business. 5x times x is 5x squared. 7 times 4 is 28. 7x and 20x is 27x. Right on the mark. Yeah, well, they're not asking for 27x in the middle. They're asking for 23x in the middle. Well, okay, let's keep going. Here's 5x. Here's 1x. Right? 5x, 1x. Okay, 5x times x. 5x times x is 5x squared. Okay, here we go. The 7 wasn't working there. Man, I wonder if it'd be working. Yeah, you put a 7 here, you get 35. It's way too big. And then you get 4, it's going to be 39. If 39 was there, I could put a 7. I could put a 7 here and a 4 here. It'd be 39. Nobody's doing that. 14, huh? Times 2. That ain't working. I don't know. Is this one of the ones that they made? There's a couple they made mistakes on, guys. They're human. We're all human. We all make mistakes. I wonder if they messed this one up. Because I don't think that I'm starting to think. Yeah, they messed it up. They messed it up. They messed it up. They should have, if they had. Yeah, they did. They messed it up. There's ways it can be done possibly. There's no way they would have answered that. It's a human thing. We make mistakes sometimes. It's the way it is. No big deal. Yeah, this thing's. Yeah, that's just wrong. What they got here is wrong. Let me make up something that works. That might work even. Yeah, they just plain messed this thing up. Was there a 4 there they should have put on there? I'm trying to think what I'm trying to like make sense out of what they did. Let me think. Trying to think what they might have done here. Yeah, this just should not have been done this way. Maybe they wanted to say this. I'm just trying to make sense out of their answers. Yeah, that's the only thing that would work. This would work according to the way they gave their answer. So let's play the game. Stay here, look at this. They would say 7, and they would say 4. I think that'd be the way to go. 4x times x is 4x squared. 4x times x is 4x squared. 7 times 4 is 28. 7x and 16x is 23x. The only way it's going to work. They meant to say that. They meant to say that. That's what they meant to say. Let's write it down. Let's write it that way. And let's take a 3x out of here. All you have to do for factorization, guys, and maybe I'm being a little cavalier about this thing. All you have to do for factorization is do the distributive principle in reverse. There you go. Okay, look at that carefully. You cannot, see right here, you can't do any cancellation. I know people like to say that. Hey, can't I just say, hey man, there's an x squared here. There's an x squared here, there's an x squared there, let me cancel. There's a 4 here, a 12 here, let me cancel. 4 goes into 12 3 times. You know, whatever. 4 goes into 12 3 times. X squared goes into x squared 1. You can't do that. You've got to do, that's why factorization is so important. You've got to factor and make whole pieces of numbers. Because then the factors, you guys, this thing right here, for example, this thing right here, that's a whole, this is like A, you know, this guy right here is like, that's A, this is B, this is C, and this is B again. Cancel, cancel. It's like you canceled the B. It becomes a whole piece of a number. The only way you can make something a whole piece of a number is if you do a factorization. Otherwise, you're not able to do cancellation. You can't do very convenient cancellation unless you have factored correctly. So let's make it, let's say it then. It's being what I did, you heard what I just said. So the whole piece, you only can do a whole piece if you got brackets and parentheses. You only can do the whole piece, ladies and gentlemen, if you have brackets and parentheses. See if they wrote that right. I mean, they might have, I seem to remember seeing something there I didn't want to see again. But no, it's okay. 39 is 3x over 4x plus 7. 3x over 4x plus 7. Okay. There it is. Yeah, they just wrote it down wrong. We're human, we make mistakes, no big deal. So we got that. They go on and they say perform the indicated operation. If possible, simplify your answer. So there's some other stuff here I'm probably not going to do. I think I did enough of this stuff up to here. And when I probably do the review for the final exam, I can get back to some of the stuff that I didn't do. We'll see how I'll see how much time I got, guys. So, I mean, we got me on film on all this stuff. So I maybe for the review for the final, I could be a little more eclectic in what I do because you've already seen all of that stuff again. You can always go back. You can always go back to the other film and see the stuff that I'm doing here. Let's do a problem like number 41. They want you to add things that look like fractions. Rational expressions are just fractions that have a lot of letters in them. So we'll see what we can do regarding that. Some of the questions that get asked are not the best. Very many of them are excellent, though. That's why I'm doing this. On occasion, there are some mistakes that are going to be present. I'm going to try to get around them and at least show you the basics of doing all the basic stuff that we know how to do. And that's what we're doing right now. We're doing okay. All right, guys, they're given, there's a problem here. Number 41. And they're asking, what if they give you this? They got x minus 9. I'm going to put it in parentheses. Always put it in parentheses, guys. Put in parentheses here. And then I want you to add this. Now, you're probably wondering, wow, how do you do that? Well, how do you add fractions, guys? You got to get a common denominator to add fractions. These are fractions also. You need a common denominator. You need a common denominator to be able to add these fractions. Minus 2x over the quantity 3x minus 27, minus that is plus the opposite. Make everything into addition. That's not a big deal. All right, no big deal. I got to talk to you. You tell me how you feel about it. You got that. Can you pull a 3 out of here? It sure looks like x minus 9, just multiplied by 3. Can you pull a 2 out of here? Guys, these look more like common denominators, almost, than you might initially think. Than you might think. This is a 1. This is a 3. This is a 2. I got an idea. Since the x minus 9, x minus 9, and x minus 9 are there, they're the same, leave them alone. Let's make them look like a common denominator. Here's a 1, here's a 3, here's a 2. Here we go. What's 1 times 3 times 2? It's 6. Each one of these is going to have a 6 on the bottom. Don't put the top yet. Each one of these has got to have a 6 on the bottom. By what did you multiply 1 to get a 6? What we're saying is, you're basically multiplying by the special 1 that we knew how to do when we did arithmetic back in the day. And of course, this marker's garbage. You multiplied the bottom by 6. Now you multiply the top by 6 too then. Special 1, 6 over 6. You multiplied the bottom here by 2. Now multiply the top by 2. Now multiply the top by 2 then. You multiplied the bottom here by 3. You multiply the top by 3. The special ones are 3 over 3, 2 over 2, 6 over 6. Okay, the way we do fractions, we're doing it with rational expressions. Multiply by 6 on top, multiply by 2 on top. Multiply by 3 on top, because you multiply by 3 on the bottom. What do you do when you add fractions? You leave the bottom alone. You leave the bottom alone. 12 and negative 4x and positive 3x is 12 plus a negative 1x. That's the argument for doing something like that. Now they try to mess with you a little bit. They try to make it a little more challenging. That's all right, we're ready. Let's do, they got 43 and 44. If you can do 43, you can do 44. If you can do 44, you can do 43. I'll just do one of them. They're saying, perform the indicated operation if possible, simplify your answer. Whenever you add or subtract fractions, you have to have a common denominator. Whenever you multiply or divide fractions, you don't need a common denominator. You do not need a common denominator whenever you multiply or divide fractions, whether there's letters in there or whether it's just the regular numbers we're used to seeing. If you multiply or divide fractions, you don't need a common denominator. When you add or subtract fractions, you do need a common denominator. Okay, so, let's keep going then. So for 43, I can't really break that guy up too much, so I'm going to put him in parentheses right off the bat. This is 6 minus x. Probably leave it like that. This is 9x squared minus 4. This is x plus 5. I'll put that in, I can't really break that up. The 5x plus 25 I can break up. I got to talk to you. So, as we look at this, a fraction divided by another fraction is the first fraction, the one that's being divided. This is a fraction. A fraction, a fraction, a fraction. A fraction divided by another fraction, then at the end, multiplied. Don't do, if there's no parentheses, they're not saying, guys, they're not saying do this first and then do division. If they said that, you'd have to do this first, and then you'd have to flip the result of all this to multiply with that. Because a fraction divided by another fraction is the first fraction left alone multiplied by the reciprocal of the fraction doing the dividing. If they said this, you'd have to do these two first, get an answer, then flip them, and then multiply. They didn't say that, though. They didn't say that here. They didn't say that here. If there's nothing present, you just go one by one. It's as simple as that. A fraction divided by another fraction is the first fraction left alone multiplied by the reciprocal of the second fraction doing the dividing. This guy stays. The last guy's the multiplication going to take place is going to take place. Got some questions to ask you. What's 5 minus 2? It's 3, isn't it? 5 minus 2 is 3. What's 2 minus 5? It's negative 3. 3 divided by negative 3 is negative 1. Wait a minute. If I got A minus B over B minus A, B minus A is really negative 1 times A minus B. And this is A minus B. That cancels, and you got 1 over -1, you got -1 as an answer. Whenever two things are reversed like that, when you do the ratio, it's -1. Let's see what we got here, guys. We try to find a good marker to nail this. See what we got. Can you pull a 4 out of here on the top? This marker actually writes, it's quite a pleasant surprise. This is 3x minus 2. I can't really do much with that. This guy right here. Kind of take a look at that. See what we can do here. All right, guys. 9x squared minus 4. I got to talk to you about it. Is the quantity 3x squared, is the quantity 3x squared 9x squared? The quantity 3x squared is 9x squared. The quantity 2 squared is that. You guys do remember that the quantity a minus b times the quantity a plus b is the same as a squared minus b squared. This guy's a lot like a, this guy's a lot like b, and so let's just do the problem. We got this, and that's important, and we got it. Okay, this right here is 3x minus 2, 3x plus 2, over 6 minus x. 6 minus x, if this was a 2, 6 minus 2 would be 4. If this was a 2, the same 2, 2 minus 6 is negative 4. 2 minus 6, negative 4. 6 minus 2, positive 4. Negative 4 divided by positive 4 is negative 1. Okay, got that in my mind. Times x plus 5. Take this guy. All right, there's a lot there. We did convert the division. We did convert the division into multiplication by flipping. We did. We got to here. These guys cancel, and you got negative 1 right here. These guys cancel. 1 over 1. These guys cancel, and you got that. What we got here, guys, is 4 times negative 1 is negative 4. over 1. We got 1 times the quantity, 3x plus 2, over 1. And we got 1 over 5. It's written a whole bunch of ways, guys, but I'd probably just write it like this. -4, leave it factored out. It's usually better if you leave stuff factored out. Whenever you're doing this kind of business, you guys, whenever you're doing this kind of business, it's good to factor things out. It's just a lot easier to look at when things are all factored out. When in doubt, and they don't really ask you otherwise, and you can do it pretty easily, just factor the stuff out. -4 times the quantity 3x plus 2 times 1. -4 times the quantity 3x plus 2 times 1 is that. 1 times 1 times 5 is this. I just see how they wrote it. They might, sometimes they make mistakes, but that should be the answer at the end of the day on this whole process. This whole thing right here, guys. This guy right here. There's your answer for the original problem here of this guy. Dividing by this is the same as multiplying by the reciprocal of this, and that's where you got to there. And that's where the multiplication takes place. That was 43. Let me just check it, guys. I'm a little apprehensive sometimes. I don't want you guys to get any kind of trouble here. 43, -4 times the 43 is the answer to it is -4 times the quantity 3x plus 2 over 5. -4 times the quantity 3x plus 2 over 5. Yeah, there it is. Good problems, guys. Good problems. There's simplify a complex fraction. Let's go with problem number 46. Almost there, guys. Almost there. We could talk more. I mean, some of this other stuff I might, like I said, when I'm doing the review problems, I might, some of the stuff that I was not able to do today on this particular work, it's relatively trivial stuff. I don't want to call it trivial. It's no math is trivial that we're doing, but it's not as complicated as the stuff that we've already done. So if I got to do a little bit of the easier stuff later on when I do the review for the final exam, stuff like that, or at least the practice review that they had, I can get to it at that point. Let me, in the meantime, knock out a few problems here, and I think we're in pretty good shape. And then I think I'll just leave it at that and go to some other stuff later on, probably when we get back together in subsequent meetings that we have. Okay, you guys see this? You can work it out. The answers are on there. Let me knock out a couple problems. I think you're going to like. Let me look at 46, 47, and 48, and that'll be it for today. And like I said, there's some other stuff I'm going to do possibly at another time. So I got ahead of the ball game on some other stuff I wanted to do. So I think we're doing pretty good. 46, 47, 48. Let's see what we can do on that. 46, there's a bunch of ways you can do it. They're saying basically, if I give you this complex fraction, why don't you break it down for me? Why don't you make it, why don't you make this thing work? 2 over x minus 5 over 2x. Okay, what do we got? They want you to simplify that. There's a number of ways you can do it. You can simplify the rational expressions on top, simplify the rational expressions on the bottom, and then go for it. Go get the answer. The number of ways you can do it here. I mean, you could say, I'm not sure maybe the best way to tell you this, but let's talk. Let's just talk a little bit. 2 over x is the same as 2 over x times the special one, 2 over 2. And 5 over 2x is 5 over 2x. 9 over 8x minus is 1 over x the same as 1 over x times 8 over 8. You're probably wondering, what am I doing? Well, I'm trying to simplify the rational expression on top, and I'm trying to simplify the rational expression on the bottom. 2 times 2 is 4. 2 times 2x is 2x. The guy here is this. Okay, we're not done, but we're getting there. 9 over 8x. 8 times 1 is 8. 8 times x is 8x. Okay. Do this. What's 4 minus 5? There you go. You got this. What is 9 minus 8? A fraction divided by another fraction. Well, we already talked about that, didn't we? A fraction divided by another fraction is the first fraction, the one that was being divided, this guy, left alone, multiplied by the reciprocal of the second fraction doing the dividing. 2 apples goes into 8 apples, you get a group of 4. How many groups of 2 apples are there in 8 apples? 4. 4 times negative 1. 4 times negative 1 is negative 4. So what they're doing here that's negative 4. Another way you could have done it is you could have taken on top, multiplied by something big to get rid of the bottom stuff. Multiplied by the same big thing down here to get rid of the bottom stuff, and it's going to give you this. That'll go too. That'll work too. Let's do 47 and 48 and call it a day, guys. 47 and 48, how would that proceed? Not too bad, actually. So let's knock it out. Okay, guys. Let's do it. Let's finish these last two. There are ways to do this. There's some do's and don'ts here you got to watch out for. It depends how the material's taught and to what level of difficulty it's going to be given when we do it. 47. They're saying, take a look. I mean, you got this guy. I'll put brackets there. Put brackets or parentheses. 1 over 7x. And I'll put this. Usually the best way to visualize what's happening guys, is through factorization oftentimes. If it's a complicated matter and there's these rational expressions everywhere, factorization tends to give you a good handle on what's going on. How am I going to add or subtract rational expressions? I need to do a valid factorization to try to get common denominators. In other places where it's multiplication and or division going on only, I don't need common denominators, but I want to get a cancellation going. Even there, I need factorization. Generally speaking, if you're adding or subtracting rational expressions, you need a common denominator, and a good way to do it is do a valid factorization to get what you need to get done. If you're multiplying or dividing, and this is all in regard to rational expressions, you guys, factorizations are always useful. They're always good to do. Well, what do we mean here? Well, there's a number of ways we can go here. There's a number of things we can go, a number of things to be aware of. And I put parentheses around there. I got this guy right here. And then I said, for this one right here, you guys, what do you say you pull a 7x out of there? I did factorization. Is it true that 7x times x is 7x squared? 7x times 2 is 14x. Sure is true. If it's true, you guessed right. Your factorization is right if it's true. 7x times x is 7x squared. 7x times 2 is 14x. Okay, so there you go. Now what? Well, I know a couple things. First of all, this whole thing goes really badly if I have division by 0. You understand, if x was equal to -2, -2 plus 2 is 0, division by 0 you would have, and then it's not the problem doesn't work. It's not defined. If x is equal to -2, this becomes 0. You're not allowed to have x equals -2. If x is equal to 0, you'd also have division by 0. Whatever the answer is, guys, in the back of my mind, x is not going to be equal to -2, and x is not going to be equal to 0. I didn't give an answer. I just told you what the answer cannot be. Okay, and that's done sometimes. It's not done other times. We'll see what people do. I've got an idea to get through this, and I think it's probably the best way to do it. The best way to do it is multiply by the same thing on each side and cancel all the denominators. You understand this big quantity, so to speak. This big quantity contains each of those. What do you say you multiply on each side by that big quantity and get everybody out of there? And remember, this can't be the final answer, but that's okay. All right. If you go 4 over x plus 2 minus 1 over 7x, two over 7x, x plus 2. Tell you what I'm going to do. I'm going to multiply by 7x times the quantity x plus 2 over 1. That's just a placeholder for me. 7x times the quantity x plus 2 over 1. I'm going to multiply by both those on each side. What's going on here? What's going on here is, this will go here, this will go there. Well, this guy's, I guess, an easy one. Him and him cancel. Him and him cancel. This is ones. So what do we got here? We got 1 times 1. We got 1 times 1 times 2. And here we got 1 times 1 times 1. 1 times 1 times 2 is 2. 1 times 1 times 1 is 1. 2 over 1 is just 2. This one comes over and you got 7x, x plus 2 over 1 times 4, x plus 2 and you're distributing this, guys. I mean, let's get that straight. Don't ever do a single cancellation here when you've got a distribution to do. Don't ever go, hey man, x plus 2, let me cancel them and it's done. No, it's done just for this guy, but the same entire thing that was originally present has to come over here. So just bring everybody over. Just play it safe. Okay? So I didn't go plus the minus like I usually do, but I will eventually. Now let's go. Now let's do it. This and this cancel. Good. Come over here. Leave this guy alone for now. This and this cancel. We got 7x times 1 times 4 is 28x. 1 times 1 is 1. 1 times 1 is 1. 28x divided by 1 is just 28x. 28x divided by 1 is 28x. 1, again, this got canceled. All of it did, right? 1 times x plus 2 over 1 times 1 let's go. 28x minus x plus 2. You could have gone and made this plus a negative. Make that a 1 right here plus a negative 1. Go ahead. 28x, distribute this guy here and here, plus negative 1x plus negative 2 equals 2. I should be done in less than 5 minutes. Or I can stay till midnight. You guys want me to keep going? I can figure it out. All right. 27x. You add these here, you add a positive 2 on each side, you get this. And yeah, it was a long song and dance, you guys. This stuff is easier done for you. You don't have to explain this to anybody. That's the teacher's job. For you, you got to explain it to yourself, and if it makes sense to you, that's when you go. That's what you're going to go with. You're going to go with the stuff that makes sense. When you're doing this, you don't have to go very rigorously explaining it to yourself. Just know what you're doing. X is equal to 4/27. Let me make sure they got that right. And also let me check myself, make sure I got it right. So for 47, that's 4/27. For problem number 47, the answer is x is equal to 4/27. Fantastic, guys. Looking good. So we got that. Let's do 48. 48 should be a little more straightforward. You're gonna do the cross multiplication I talked to you guys about last time that we were together. We saw like 48. And this will be the last problem on this one. Like I said, some other stuff I can probably talk to you about regarding this stuff. We can see it when we do we do the practice for the old final exam that they had, the old stuff that they had. So we got 3x plus 5, the quantity 3x plus 5, the quantity 7x minus 8, and here we got 16 over 9. Well, this is a lot easier than you think. It's a lot easier than the other one. Put this as a whole quantity. Put that as a whole quantity. That's it. Solve that equation. How do you do it? It's just a proportion, you guys. I am going to do this. I am going to cross multiply here, cross multiply there. I've got, at the end of the day, 9 times 3x plus 5. I'm sorry, 9 times the quantity, 3x plus 5. And I got 16 times the quantity, 7x minus 8. Let's see what I got. Let's distribute this throughout, guys, and see what we have. Let's take this, and we get 112x. Take this, we get 128 minus 128, or plus a negative 128. Just make sure everything's on the mark here, guys. We've got, yeah, everything's on the mark. I think we got 70x, 70, 112, you got it. Okay, let's go. Let me subtract 27x on each side. I'm going to subtract 27x on each side and get 85. Let me add a positive 128 on each side and get 173. Make sure it's on the mark here, guys. Yeah, 173. Divide by 85, and you got 173 divided by 85. That can be written as 2 3/85. A lot of ways you can write it, etc., etc. Make that a little bit bigger here, guys. 2 3/85, or just this. I probably would just leave it right here. Let's see how they answered it at the end, and then we're done. That was 48. Right, and that's how they left it. They left it like this, like I thought they would. They left it at what? They left it as 173 divided by 85, and that's fine. It's all good. All right, guys, that's a line share of what you want to know for the old practice test number 2 that I have on there for you guys. Old practice test number 2 pertaining to intermediate algebra. I hope it helps you guys out. Sounds like a plan. I'll see you guys soon. Take care. Thank you.